So I believe that today will be an interesting day. We were working hard to do a couple of things. One is to debunk some common misconceptions. And this is very important. I mean, 2 days ago when I was finalizing these intro slides, I figured out that maybe there is a reason, which is more emotional reason, why more people don't work in memory systems. Why don't many people just accept it? It's, it's something bad, but there is nothing I can do about it. Today, we will try to show you that there is something you can do about it. There is a lot you can do about this, okay? So that's it. So this is the one. I mean, if you read, long DRAM latency continues to be the critical performance bottleneck in modern systems. And actually, I asked ChatGPT about this, and I found references to theses of very important teams that say this, and a lot of people believe in this. I will not ask you to raise hands who believed in this, but a lot of people believe in this. And this is sort of true, but maybe not completely true, okay? Cool. The next thing, we will try to demystify memory system performance. So I'm in this business for 12 years. I talk with a lot of people who come and say, my application is memory bound. And you say, okay, let's talk. And then we enter in some explanation that looks like voodoo to me, right? And it's not fault of the person, it's simply what, okay. But it's like, and what we will try to do today, to move this abstract and esoteric memory bound concept or memory performance concept into something more tangible. And if we succeed it's good, because you will feel it a bit more. Okay? So I'm excited. Okay? We have very interesting lectures today from different domains, looking at the same problem through different angles. The preparation of the course was very interesting because we started from different points. And something that I really liked is that people from different angles wanted to do something similar-ish, wanted to do something together. We were not stuck in our bunker saying, no, this is my tool, it's the best, and your tool is okay, but we're like, interesting, different angle. Okay? And very interesting audience. Okay? So we have a wide range of people in the room. We have people who got their PhDs in 1990s and who got their birth certificate in 2000s. Okay? So don't expect one-size-fits-all course. Don't expect that all the lectures are for you. Some of them will not. Something will be too easy, something will be too difficult, but that is okay. If you leave this course with something useful, it's good for you, okay? But there are some things that do fit all, and this is coffee break. Right? So we have the first one in 2 slots, right? So we'll have coffee break, 30 minutes, Vectex Garden. Okay? Until yesterday, in theory, we had a sunny day. Well, today is not the most sunny day, but don't mind, guys, go to Netherlands for a couple of weeks. It will look much better, okay? So long networking event or after party or after work, whatever, after the course, right? So you sum this and you say, this is 4 hours, man. So you're 4 hours, you're wasting my 4 hours of the day. Instead of giving me more lectures, more slides, more Python script, you're giving me whatever, food, coffee, and sugar, right? So, but that's the point. I mean, the course is not only what happens here. I believe important part of the course what happens in Vectex Garden. Okay? So use this time to hunt the lectures, talk with them, ask questions. Okay? And important thing is maybe the most important person for you is not the person who will show the slides today, but the person sitting next to you. Okay? So there are, whatever, 60 people in the room. So you can talk with 60 minus 1. And not all of them are idiots, okay? And at least there are 5 people in the room who have similar interests as you, who have similar problems as you, who want to do the same thing as you. So talk. Maybe you don't find them in the first coffee break, but then there is queue for food, you will find them. Okay. Cool. So Zoom. Another big apology for people at Zoom. And again, we did what we could. We did what we could. Until 2 weeks ago, we had a room of 20 people. So it was not trivial to get this one and other ones. Okay? So just to give you an idea, I don't know whether you see this, but this is the email that I sent to Jana mid-2025. So two things you could see on this email. Number one is the organization of this course started some time ago, okay? And what you see in yellow is I would expect around 20 people. So my performance estimates, I hope, are somewhat better than this one. Right? So we didn't expect this. Okay, let's see what we take out of this. This is the first iteration of this course. Let's see what we'll do later. Okay, so important mindset I would like you to have is that don't think about end of a session as an end. This is just the beginning of your journey. Let's take Roofline as example. This is something that will follow, right? It's like, okay, so they will finish at whatever, 11:30 or whatever. And that's it. There are two things you can do. You can say, tick, Roofline done, next. Or you can say, okay, this is interesting. Maybe this is useful for me. Tell me more. And you can go to tell me no more. If you go to the course webpage, you will find sources that they provided or we checked with them. So there are sources that make sense, probably, right? Another important thing is you will get contact of these people. So you will have their face, they are in the room, you will have 4 hours with them, having coffees, putting sugar in you, whatever. And so that's great. I mean, we are giving you today a great intro to your future email to these guys. Saying, hey, Leonel, I attended the Roofline lecture on this memory course and I liked it, but I have some doubts, can you help? It's a good intro. So it's not completely cold door entrance. And don't stop with, I have a question, right? Think. Do you want to do a PhD? You want to do whatever, right? Contact these guys. Cool. Another thing that is, I think, important part of the course, and it could look a bit boring, is you have seen that planning of this course started some time ago. Now we are planning follow-up trainings. Okay? So today this is done, right? Today we deliver. But we already started to think what next. And your opinion is important. We will have 2 questionnaires today. And this is one of the few things that I would kindly ask you to do, is to fill these questionnaires. We will do some part of this here, right? So you do now, and you tell us, right, a bit of who you are, so you can think in next hour who you are. Are you a student, professor, researcher, whatever? What do you do? And then we will ask you 3 questions about each of the tools that you will see today. One is, how familiar was this for you before today? And there is no good or bad answer. It's simply, I was aware of this, I was not aware. Fine, right? Another thing is, how was the presentation? Easy, about right, a bit too complex. And again, there is no good or bad answer. We want to touch the temperature of the room. And would you like a follow-up training on this? And again, tell us what you think. This is very important. We will have one about Intel tools that I believe deserve special attention, and we will have one general of the course, right? And based on your input, we will decide what to do next. So your opinion will be heard. It's not that this will go to some folder and we send it to some bureaucrat and nobody sees. No. I will take this very seriously and I will hunt people who presented today with the outcomes of this, okay? So that's it. Okay, so we have arrived to the motivation part, why memory systems are important. And I was trying to present this for years, and I think that I found a single slide way to do this. So this is your server, okay? And let's see what happens in your server when it does different things, okay? So this was INTED. Has anybody seen INTED? Okay, Claudia, yeah, but this is your 3rd course. So this is not INTED, this is fun. Okay, this is no. So INTED, let's go again. So INTED, this was INTED. One cycle, something happened. You have 2 operands, you do something. Okay, so this is, okay, short operation, fine. Let's do what happens with long operations. Right, floating point divide, that's the nasty one. And then you say, okay, so That's it. Okay? A bit more suffering. Fine. Okay. Let's see what happens when you need your data. When your data is not in your register, but it's somewhere else. Okay? And that somewhere else is typically your caches. Okay? You know this. So let's do L1 cache. Okay, that's it. Let's say 10 cycles. Okay? And now let's see what happens when you go to the main memory. Oh, done. Okay, so we have 4 hours of coffee breaks and lunches and half an hour of demo what happens when you go to the main memory. So, did everybody see it? I mean, this is number one. I mean, INTED was a bit tricky to see. Main memory was cool. No need to repeat. Okay? So this is what you, if machines feel anything, this is a suffering that your load feels when it has to go to the main memory. Okay? So does anybody have a doubt that main memory is important? Thank you. So, but you're smart people, so you will say, you're cheating. 99% of my access will hit the caches, right? So what you show me here is, happens from time to time, I don't care, right? And this brings us to the paper that many people cite, not many people understand. The memory wallpaper. The famous memory wallpaper. Wolf and McKee, 1994 and 1995, depends which one you take, okay? So what this paper tells you, and please read it carefully, if there is one paper that you should read, it's this paper. What it says, and I will tell you what it says because this is what Sally wrote 20 years later. We worked with her. And effectively, it is telling you, even with cache hit rates above 99%, relative memory latencies would soon be so large that the processor would essentially always be waiting for the memory, which amounts to hitting the wall. This is what the paper is all about. Many people cite it with some different statements. So effectively what it's telling you is, okay, even if only 1% of your loads suffers what happened on the previous slide, this is still killing your performance a lot. And they propose, they show some very simple model. It's 4 pages paper, very simple. Even they call it implications of the obvious. Yeah, they thought it's obvious. So even if only a small percent of this, even with all latency techniques, that latency tolerant techniques that we do, this is still killing you guys. Okay? So actually, there is no one memory wallpaper. There are 3 of them. This is the original one. This is 10 years later. It's worth reading. And this is I like this one, not because, also because we were part of the story, but because in this paper, this is the quote that you have seen on the previous page. This is where Sally was talking about her work 20 years before. 20 years is a lot of time. Gives you perspective. Is it still valid? It is not valid. What's happening? She also tells, why did we do the original paper? And it's worth reading it. Cool. So this course is a spin-off from course on heterogeneous memory systems that BSC was doing, accelerators teams was doing for 9 years. And they asked me to give the intro to this problem, okay? So what I was doing is I was trying to touch the temperature of the room, Okay, so you see this is slide number 4, and they just come, hey guys, I will give you a task. Just to see how people think, just to see where we are. And the task was very simple. So individual, just think about this, daydream about this, write down the answer if you want, whatever. So you have one high-end server. Let's imagine Intel, with whatever default DIMMs are, DDR4, DDR5, I don't care, right? You select your favorite benchmark, and then you run application on that server. Everything fits in this DDR4, that's it. So now you put some sexy memory to your server. And in that time, sexy memory was Optane. But select your favorite sexy memory. And that's something, so okay, so now you put Optane in your server, and then you spend some time, 3-6 months, optimizing your application for this now exotic, sexy memory system. And tell me how much would you improve? What is your estimate? And the estimates that I got, I remember the last one, were everything between 5% and 10x. Okay? And they were, for this particular case, they were all wrong. A lot. Okay? But this is not important. This is not about whether something is right or wrong. What I figured out is that a lot of people in the room are so focused about the solution, or how will I optimize this? I will use Linux kernel, whatever. I will use AI method, whatever. But people did not think about the problem. What is really the performance of my baseline memory? What is really the performance of this new sexy memory? Where is my application in all this domain? Okay? So here is one quote that I think it really represents well what would be my advice to you. Think about the problem first. Understand the problem. Don't rush into a solution, into AI scheduler, right? Understand the problem. And this is what we will try to do today. And if we just come to this point where you understand a bit more what is memory system performance, or why it is problematic for your app, we succeed. Cool. Another, since we are quoting Albert Einstein, this is another quote that I think it's very relevant. A lot of people were thinking about memory system in terms high performance memory. It's esoteric for me. What does it mean, high performance? Low performance. Big and slow, fast and whatever. Small, whatever it is. Right? I mean, if you want to do, if you don't care about memory, that's super okay. I'm saying it's too simple. Maybe it's not. Simply not everybody has to care about this. But if you want to work in area of memory systems, if you want to adopt new technologies, if you want to touch heterogeneous memory systems, if you want to do performance analysis, whatever, this is not enough, guys. Sorry, it's not enough. And what I believe, and this is maybe too strong, I'm happy to discuss this, that the course today is as simple as possible. Or at least you should get 80% of the course today. And then enter into the problem, enter into whatever solution is. And maybe it's boring for some of you, but I think it's fundamental. If you don't cover this, you won't reach far. Cool. Brutal misconception. And this will be, I wrote this slide, I did 2 nights ago. It was 1 a.m. or 2 a.m., okay? But it was something that bothered me, so I'm not even sure it's 100% correct, but I'm pretty sure I'm onto something here. So many of you, I believe DRAM latency is constant for decades. You have heard this. I'm sure that at least half of you in the room heard this, because I have heard it 10 times. And then you have also heard that therefore the long DRAM latency continues to be a critical performance bottleneck in modern systems. You have also heard this. And I actually put this in ChatGPT or something similar, and I found the thesis and the papers that were constantly saying this. But what I will argue in the next 2 slides is that this is wrong. Very wrong. That this is a sin of memory system community that really pushed a lot of people out. Okay? So stay with me. Okay? So the truth is a bit more complex. And I will read this. And if I need your attention, this is next 2 minutes. Okay? So this is the paper we did. This is a paper we did 5 years ago with people who know memory. IBM, Micron, and people who know memory. So one of the things that we wrote in this paper, it was sort of motivation for processing in memory, blah, blah, but this is not relevant. What is relevant, I believe, are two paragraphs. And this was written, I believe, by myself and Paolo. And Paolo is from Micron, he knows. And I believe that I know a bit. So what does it say? So the high latency, let's start with latency, of main memory is often thought to be a consequence of memory technology. Memory technology effectively means cell. What is your memory cell? How do you store 1 bit of data? Which in DRAM is effectively capacitor, which effectively is a bucket of electrons. You just push some electrons into a bucket and you hope they will stay there for some time. And then you come back and you see, hey, my bucket is empty or my bucket is full, 0, 1, 1, 0, whatever, okay? So that is the timing parameters associated to the memory cell or cell arrays. This is what I told you. Cell is a bucket of electrons. So this is what DRAM latency is constant for decades, and this is what this is saying. This is the statement you have above. So effectively, people blame cell, memory cell. Okay, but, and this is a very strong statement. I mean, it sounds something we could write here, but I like it. This is wrong. Okay, so what we say, in fact, most of the main memory access latency does not come from the time required to access the memory cells, but from the overall complexity of the memory system in both hardware and software, with example of virtual memory translation. And then let's go deeper, right? So internal memory latency of DDR3, DDR4, so this was 5 years ago, this is what we had, right? It could be as low as 15 nanoseconds. Trust us, this is like that, okay? And it is indeed constant for decades. So, but what do we talk about? So this is your DIMM. This is typically green, you know, you can probably see this, you have it in your laptop. This is black, this is a chip, and this is a copper, right? This is what you plug into. So this is your DIMM. This is typical memory. When I think of memory, this is what I remember. So these 15 nanoseconds, this is the latency of the cell. You touch whether your bucket of electrons is full or empty. Okay, this is 15, 1, 5. Okay? So, and this is what is, okay, fine. The external memory access latency. And this is the main memory latency perceived by the user. So this is what you suffered 5 slides ago. This is this external latency. Is the time required for a load instruction to access data in the main memory. We typically call this load to use latency. So I load and until I can use the data. Okay? So is the time blah, 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 blah. This timing is platform specific. Okay. Okay, so this is very, okay, so it is constant for decades or it is platform specific, okay? So it's not constant. And includes the time spent in the CPU, check this, and this is just a summary. CPU load store queues, cache hierarchy, network on chip memory controller. There are some copper wires, you know, between your CPU and memory, right? And in current architecture, the minimum blah, blah, blah corresponding is 90 nanoseconds. And actually in that system, it was between 90 and 285 nanoseconds. So now compare this 15, 1.5, with 90 to 285. So what I believe it's important for you to understand is that the misconception is that the problem is here. The problem is in the DRAM technology, right? The problem is in the cell. Right? But this is 15 nanoseconds. Your load to use latency in the current system is between 100 and 500. Puya will show you this later. So, but what I'm telling you is, guys, that the real problem is here. If you get this, let's have a coffee break, let's go home. It's enough, okay? And this is, so why is this important? You can say, okay, get a life, okay? Okay, you prove your point, nice, get a life. But I believe it is important. And because it has a very serious side effect. And this is that feeling, there is nothing I can do about it. You know, because when we come to this cell latency, this is physics, guys. There is nothing you can do, okay? If something is constant for 3 decades, guess what? You're not going to change it. So then you come and say, you know what? It's constant for 3 decades. It's really physics. I don't understand physics. They are weirdos. I don't want that. So nothing, just leave it. Memory is my problem, but there is nothing I can do. And what this is learned helplessness. Just give up, suffer. You know. What we will show you today is, and I have felt this with people, and I was thinking for a long time, why people are like this? And my hypothesis is in the last 2 slides. So what we will show you today, and I think that this is brutal, is that there is so much you can do about this. Guys, you could not be more wrong that there is nothing you can do, right? Because what you will see is that the memory access latency that matters, that you care about, that you suffered 5 slides ago, is so not constant. It is different in different systems. It is different in the same system, depending on how you use it, and you will see the differences. The range is huge. The numbers are huge. And that's it. You can do a lot of it. But the step 1 is to understand it. And this is what we will try to do today. Okay? Cool. So memory bandwidth, just 2 teasers. One is, we will cover this also later. Mariana will take care of this. So check this. You have the memory system bandwidth in your data sheet. It is 100 gigabytes per second. John, I have your attention. Yeah, good. So your application uses 70 gigabytes per second. Do you need more bandwidth? It's a tricky one. No, don't answer. No hands, whatever. Just think about this, right? The way I understand this is, you know, I'm listening my phone on 70% volume. And so should I buy a new headset? No, man, it's 70% volume. I mean, I don't know. I have still 30% to go. But you're too smart for me. So we can say, okay, yes. But data sheets is theoretical, right? And what you actually get may not be 100, right? So you will get maybe, so let's say you run your bandwidth-hungry benchmarks, for example, stream, and you get 75. And your application is using 70. Okay, fair point, right? But still, my question is the same. My volume goes up to 75, I'm at 70. Should I buy a new headset? And it's not trivial to get this. Mariana will try to make this clearer for you. And I hope that if you have this clearer, you will understand so much what is happening with your application in the system. Cool. So what will you get today? We are at the intro stage. Then we have the main part of the course are the tools. We'll go with the roofline, the most widely used memory-related performance tool. I'm very happy that we have guys from Ines, from Lisbon. They came here for this. And these are the guys who invented and then also deployed in Intel tools cache-aware roofline model. So they have how many? 20 years in rooflines? Man, get the life. So that's it. You have interesting lectures. It's not that they read a paper and, I mean, they know, they probably made all mistakes you could make. So then we have 2 tools, which is one is mass, one is profit. They are a family of the tools that is based on bandwidth latency curves in memory systems. Okay, that is coming next. But before that, we have a coffee break. And then after that, we will have lunch. Take this lunch. Take it easy. Take coffee, you will need it. But what comes next is the top-down, which is, in my opinion, the most powerful, but also the most complex performance tool that we have. So you will need attention for this. And then after that, we will touch advanced memory systems with a short intro of heterogeneous memory systems, which is something that is happening today. It was with us for some time, but just in case you want to know, Tony will give us the intro, and then we will have a short panel discussion. But the panel discussion won't be for all people here and whatever, saying what we have to say. We already have the whole day to say what we have to say, but it will be more pointing on you guys. Saying, okay, how was the course, right? What are the comments? What are the questions? What did you miss? Okay, and so this will be also questionnaire number 1. Questionnaire number 2 will be right after the Intel tools. Please fill them. Okay, so tools, slides, we will have roughly the following outline. We will start with general ideas, with fundamentals. Okay, so this is what you have to understand in order to use the tool. So don't just click, you know? Don't just type Python. Understand what are you doing, okay? And then we will have system profiling part. System is your hardware profiling. So you have a box. Your application is not on the box yet. Profile this. What is the performance profile of this? And then add your favorite application. And it is fundamental that you distinguish between two. So number one is this is your hardware with whatever system software is running, but your app is not there yet. What is the performance signature of this thing? Okay? And then add your app and figure out what is the performance of your app. And then figure out how can you put this together. Okay? And then we will have a bit more advanced level, which is demo that you will see today, provided by material for the hands-on that you can see, we can do later today or tomorrow or never. And we will give you the pointers for if you want to explore more. So this is the general idea. Okay? So again, it's not the end of the course, is not the end of the journey. We hope it's the beginning. Cool. We will answer two important questions that are, again, very different questions. And many people don't see the other one. I mean, many people are in one question, but they don't see the other one. It's important to understand that there are two of them. So number one is, which memory system should I select for my application? And you can tell me, dude, there is nothing to select. You know, this is the node, this is what they run, that's it. And you could not be more wrong. What you will see today, that even in Mare Nostrum today, you can select a lot of things. And you will see that different nodes with slightly different memories have somewhat or slightly or a lot very different performance. So that is important for you to get, okay? Another, and you have, this is for example, MR DIMMs, which is super sexy technology. If this DIMM looks weird, it is because it is weird, right? And then you have HBM, you know this, CXL memory expanders, all different flavors of exotic memories. Okay? And we will try to put their performance down to earth for you guys. The second question is, and I believe that this is interesting for majority of the people in the room, can I optimize my application for a given memory system? Mare Nostrum 5, general purpose node, whatever, my application. It seems that memory is a part of the problem. What can you do about it, okay? But here I have two sub-questions. A lot of people run into the question, is there anything I can do about it? I believe that the first you should try to understand where is my performance problem. And you will see a lot of tools that you can do today. Cool, that's it. I mean, I honestly believe this. I told this to Alexander yesterday, he was laughing. And I really believe that we have the best memory-related tools presented by one of the best people that can do it. And something that I'm really happy to see that we had different views to the same thing, but we are in the same room, the same day, trying to give you a story. So that is, I think, being inclusive. And cool, thank you. And I will go super fast about this. Support from different projects, from different institutions. This course would not be the same without them. These are the people who will present or participate in the tech program, and also people from education who really helped a lot to organize everything. And some people who are not today, not today with us, and it's not the best away or anything. They're just traveling, you know. So it's, but who really supported this. And who really, I really like Mikhail and Osman because they're computer architects and they're driving projects that are building chips and so on. So maybe performance analysis is not their main concern. But when I pitched this course to them, they said, all in. All in. And this is what they did. So that's it. And thank you. And thank you all. Thank you for being here. Thank you for your patience. And please stay with us. If you want any contact, this is easier to remember than my name and surname. So let's go. Thanks. What is the time slot? We are great. So we go 1 or 2 quick questions, and then we go with the roofline. Roofline guys, come. Let's go. Thanks. Stay with us. 1 slot to go, and then a coffee break.